Hello, and welcome to Sleep with Science. Before we begin, I'd love to know, where are you listening or watching from tonight? Maybe you're lying in your bed, letting the quiet of the night take over. Maybe you're somewhere far away, headphones on, looking at the stars. Wherever you are, tonight we're going to explore something invisible, something that exists underneath everything you've ever touched, seen, or imagined. This is the world of quantum physics, the world that hides beneath what we call reality, the illusion of solidity. Take a moment to look around you, your room, your phone, your hands. Everything seems solid, stable, and motionless. But that's an illusion. If you could shrink yourself 1 billion times smaller, small enough to stand on the surface of an atom, you'd see that the world is made not of stillness, but of motion. Everything vibrates. Everything moves. An atom, the building block of matter, is almost entirely empty space. At its center sits the nucleus, containing protons and neutrons. Around it, electrons dance, not like tiny planets circling a sun, but like hazy clouds of probability, shimmering, uncertain, always moving. To give you a sense of scale, if an atom were the size of a football stadium, the nucleus would be like a grain of rice in the middle of the field. The electrons would be tiny specks zipping through the stands, and everything else would be pure emptiness. The world we call solid is built on emptiness and energy. It's like a structure made of invisible scaffolding, so well organized that we mistake it for something solid. The birth of the quantum world. At the end of the 19th century, scientists believed they had figured it all out. Newton's laws explained motion. Maxwell's equations explained electricity and magnetism. The universe, it seemed, was a perfect machine running like clockwork. But then, cracks began to appear. Experiments started showing that light and matter didn't behave the way classical physics predicted. A German physicist named Max Planck was studying something simple: how objects glow when heated. He noticed that when you heat metal, it glows red, then orange, then white. But his equations couldn't explain why the glow changed color with temperature. So, he made a daring assumption. Maybe energy isn't continuous. Maybe it comes in small, indivisible packets, quanta. That idea, one simple equation, was the seed of an entirely new universe. It meant that energy wasn't a smooth wave, but a staircase, existing only in specific steps. This discovery broke open physics. It told us that reality, at its smallest scale, is not smooth, but pixelated, like a digital screen made of tiny points. Planck didn't know it yet, but he had opened the door to quantum mechanics, a new kind of physics where nothing behaves as it should. Light bulb light, the first mystery. A few years later, Albert Einstein expanded Planck's idea while studying the photoelectric effect, when light hits a metal and ejects electrons. Classical theory said brighter light should knock out more electrons. But that wasn't what happened. Only certain frequencies of light worked, no matter how bright the light was. Einstein realized that light wasn't just a wave. It was also made of particles, little packets of energy called photons. Imagine light as a gentle rain of energy, each drop carrying a punch strong enough to knock an electron loose. That was revolutionary. Einstein had just shown that light, something that fills our sky, that powers our world, was both a wave and a particle. And that contradiction became the foundation of quantum physics, the strange duality. So which is it? Is light a wave, or is it a particle? The answer is both. Or maybe neither. It depends on how you look at it. In the quantum world, objects don't fit into neat categories. They behave like waves when unobserved and like particles when measured. This idea, called wave-particle duality, completely shattered our understanding of reality. To visualize it, think of the double-slit experiment, one of the most famous in science. When scientists fired light through two slits onto a screen, they saw interference patterns, proof that light behaves like a wave. But when they fired one photon at a time, the pattern still formed, as if each photon went through both slits at once. It was as if reality itself refused to choose a single state until we forced it to. When we looked at the experiment, when we measured it, the photons acted like particles, picking one slit or the other. When we didn't, they acted like waves, exploring all possibilities. Observation changed the outcome. Just by watching, we altered reality. That's not philosophy, that's physics. The hidden dance. Let's go deeper. At the atomic level, electrons don't orbit like planets. They exist as probability clouds. Their location isn't fixed. It's described by a wave function, a mathematical expression that tells us where the electron might be. When we don't measure it, the electron exists everywhere its wave function allows. When we measure, the wave function collapses, and the electron chooses a single location. This collapse is one of the great mysteries of physics. It suggests that particles exist in a superposition, multiple states at once, until observed. You might be tempted to ask, does that mean the universe doesn't exist until we look at it? Even Einstein struggled with this question. He famously said, "I like to think the moon is there even if I'm not looking at it." But quantum physics doesn't care about comfort. It tells us, on the smallest scale, existence is not definite, it's potential. Reality is a collection of probabilities waiting to be realized. The beginning of understanding. Every technological revolution of the 20th and 21st century, from lasers, computers, and transistors to quantum computers, comes from this strange understanding of the quantum world. We learned to use uncertainty rather than fight it. We built devices that rely on electrons tunneling through barriers, particles teleporting through space, and waves interfering to create new possibilities. Quantum physics doesn't just describe the world, it creates the world we live in. Yet even now, more than a century later, no one truly understands why it works. Physicist Richard Feynman once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." And perhaps that's the most beautiful thing about it. The universe, in its smallest details, is still a mystery. Shimmering, unpredictable, endlessly fascinating. In the next part, we'll dive deeper into how this strange world works, how matter forms, how probability shapes everything, and how the act of observation connects us to the fabric of reality. The quantum revolution. The cracks in classical physics. By the late 1800s, scientists believed the universe was complete. They had Newton's laws to describe motion and gravity. They had Maxwell's equations to explain light, electricity, and magnetism. To many physicists, nature was a grand machine, running like perfect clockwork. But a few small problems, tiny, almost invisible, began to appear. And as history often shows, it's the smallest questions that break open the biggest mysteries. One such problem was something called the ultraviolet catastrophe. Scientists noticed that when they heated up objects, metal rods, for instance, they glowed red, then orange, then white. But the equations of classical physics predicted something impossible, that at high frequencies, hot objects should emit infinite energy. Infinite. Of course, that didn't happen, or the universe would have burned itself apart long ago. It was Max Planck, a quiet German physicist, who decided to fix this. He proposed a radical idea. Perhaps energy doesn't flow continuously, like water, but instead comes in tiny packets, which he called quanta. This simple concept changed the world. By saying energy was quantized, Planck unknowingly opened the door to a new dimension of physics, a world where continuity breaks into discreteness, and the smooth universe of Newton becomes the pixelated universe of the quantum. Planck's constant and the birth of quantum thought. Planck's idea came with a new number, a constant that became one of the cornerstones of modern physics. H equals 6.626 times 10 superscript 3 joule seconds. It might look small, but it's enormous in importance. It defines the graininess of reality. If you zoom into nature far enough, Planck's constant marks the smallest step possible, the quantum of action. Below that scale, the universe stops behaving like a machine and starts behaving like a mystery. Planck didn't fully believe his own idea. He thought it was just a trick to make the math work. But within a few years, others realized it was far more than that. It was the beginning of a new reality. Einstein and the photon. A young Albert Einstein, not yet famous, was fascinated by Planck's work. He took it one step further. He proposed that light itself wasn't just a wave of energy, but was made of quanta, tiny packets that he called photons. This helped explain the photoelectric effect, where light hitting a metal surface knocks electrons loose. According to classical theory, brighter light should eject more electrons. But that wasn't true. Only higher frequency light, like ultraviolet, worked regardless of brightness. Einstein realized why. The energy of each photon depends on its frequency. Blue light photons carry more energy than red ones. If a photon doesn't have enough energy, no amount of brightness can make up for it. This was the birth of the photon, and it forever changed how we see light. Light was no longer just a wave, it was both wave and particle. A paradox made real. The rise of the quantum pioneers. Soon, a wave of brilliant minds began to explore this strange new world. Among them were Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and later Richard Feynman. They weren't just scientists, they were explorers, diving into the unseen, armed only with mathematics and imagination. Each of them saw the quantum world differently. Bohr believed that nature itself was probabilistic, that certainty was an illusion. Schrödinger saw waves and wanted to describe how they evolve in time. Heisenberg focused on what can be known and what can't, leading to his famous uncertainty principle. Together, their work became the foundation of quantum mechanics, the theory that describes the behavior of everything that's too small to see. Bohr's atom, a new model of matter. Let's travel back to 1913. Niels Bohr was trying to solve a mystery. Why do atoms emit light at specific colors? When you heat hydrogen gas, it doesn't glow continuously. It glows in distinct lines, called spectral lines. Each color represents a specific energy jump inside the atom. Bohr proposed that electrons orbit the nucleus in quantized energy levels. They can jump between these levels, but they can't exist in between. When an electron jumps down to a lower orbit, it emits a photon, a packet of light whose energy equals the difference between those levels. This explained the strange emission lines perfectly. Atoms, it turned out, were not miniature solar systems. They were quantum machines, with rules that allowed only certain movements, certain energies, certain possibilities. Bohr's model became the first great victory of quantum theory. Schrödinger's waves. A few years later, Erwin Schrödinger expanded Bohr's vision. He imagined particles not as dots, but as waves of probability. He wrote down an equation. one of the most beautiful in all of science, the Schrödinger equation. It describes how the wave function of a particle changes over time. The wave function, symbolized by the Greek letter psi, tells us everything we can know about a quantum system. But it doesn't tell us definite outcomes, only probabilities. If we could see an electron's wave function, it would look like a soft mist surrounding the nucleus, denser where the electron is more likely to be found. But here's the strange part. When we observe the electron, that mist collapses into a single point. Before we look, it's spread out. After we look, it's one place. That collapse remains one of the deepest mysteries in physics. Heisenberg's uncertainty. In 1927, Werner Heisenberg added another layer of strangeness. He discovered that you can never know both the position and momentum of a particle exactly at the same time. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our tools, it's a property of nature itself. It means that on the quantum level, reality is fuzzy. Particles don't have fixed locations until we measure them. This principle explains why electrons don't crash into nuclei. Their uncertainty keeps them in motion, like a blur that can never settle down. Uncertainty, rather than chaos, is what holds the universe together. The quantum field, a deeper layer. As quantum theory matured, physicists began to realize that particles aren't tiny objects. They're excitations in invisible fields that fill space. Every type of particle, electron, photon, quark, corresponds to its own quantum field. You can imagine these fields as vast oceans spread across the universe. A particle is just a ripple, a temporary vibration in that field. This idea led to quantum field theory, or QFT, one of the most successful scientific frameworks ever created. It explains not just particles, but their interactions, the forces that govern matter. Electromagnetism, the strong nuclear force, and the weak nuclear force, all are beautifully described by this theory. Gravity remains the one force not yet unified, but researchers continue to search for a theory of everything. The final bridge between the cosmic and the quantum. The quantum imagination. Quantum mechanics doesn't just describe the universe, it changes how we think about it. It tells us that reality is not made of things, but of possibilities. That everything, even space itself, is a vibrating ocean of energy and information. It tells us that the line between observer and observed may not exist, that the universe might, in some deep sense, be aware of itself. These ideas inspired generations of scientists, philosophers, and artists. Without quantum physics, we wouldn't have computers, lasers, smartphones, GPS, MRI scanners, or the dream of quantum computing and teleportation. Every piece of technology that defines our world began with people asking the strangest questions imaginable, toward a new understanding. By the mid-20th century, the quantum revolution was complete. What began as an attempt to explain glowing metal had evolved into a theory that could describe the entire universe, from the tiniest subatomic particle to the cosmic microwave background. But the story is far from over. Because the deeper we look, the stranger it gets. We still don't fully understand what the wave function truly represents. We don't know if the collapse is real, or if every possibility actually happens in some parallel universe, as the many worlds interpretation suggests. In quantum physics, every question answered creates 10 more. In Part 3, we'll journey further into quantum entanglement, non-locality, and the eerie connections that bind particles across space and time. We'll explore the experiments that prove the universe isn't local, that information might travel faster than light, and that reality itself might be woven together in ways we can barely imagine. So, take a deep breath. Let your thoughts drift through the fabric of space and energy. The universe is about to get even stranger. This was part 2 of quantum physics, explained slowly. Part 3, the spooky action at a distance. Tonight, we explore one of the strangest, most beautiful, and most puzzling ideas in all of science. An idea so mysterious that Einstein himself called it spooky action at a distance. This is the story of quantum entanglement, the invisible thread that ties particles together no matter how far apart they are. So take a deep breath. Let your thoughts drift beyond the surface of reality. We're about to enter the quantum web, a place where separation is an illusion. The quantum web begins. To understand entanglement, we need to revisit something fundamental, the wave function. In the quantum world, everything, electrons, photons, even atoms, can be described as a wave of probability. This wave tells us not where the particle is, but where it could be. When two particles interact, for example, when one electron collides with another, their wave functions can become linked. They merge into a single, shared description of reality. From that moment on, they are no longer two separate systems. They are entangled. Whatever happens to one will instantly affect the other, even if they're light years apart. What is entanglement? Imagine this. You have a pair of gloves, one left, one right. You put them into two boxes, seal them, and send one box to Mars and keep the other on Earth. When you open your box and find the left glove, you instantly know the other one is right, even across millions of kilometers. That's not spooky, that's just logic. But here's the difference. In the quantum version, neither glove has a definite side until you open one box. Both are in a strange mixture, part left, part right, until observation forces the choice. And when you open one, the other instantly decides, too, faster than light could ever travel. It's as if the universe itself whispers between them, "Now you must match." Einstein's problem. Albert Einstein didn't like this idea. In 1935, along with Boris Podolsky and Nathan Rosen, he wrote a paper, now famous as the EPR paradox. They argued that if quantum mechanics were complete, it must mean two distant particles could influence each other instantly. That would violate one of Einstein's most sacred beliefs. Nothing can travel faster than the speed of light. He believed there must be hidden variables, secret factors that determine the particle states before measurement. We just couldn't see them yet. In his view, quantum mechanics wasn't wrong, just unfinished. It was spooky, yes, but only because we didn't yet understand what was underneath. He called it Spukhaft Fernwerkum, spooky action at a distance. For decades, the world agreed with Einstein. Surely nature couldn't be that weird, could it? The challenge of John Bell. Then came John Stuart Bell, a quiet Irish physicist who worked at CERN in the 1960s. Bell didn't try to dismiss Einstein's doubts. He tested them mathematically. He asked, can hidden variables explain entanglement while keeping the world local? Meaning nothing travels faster than light? Bell derived an inequality, a kind of mathematical boundary. If the universe followed local realism, experimental results would always stay within that boundary. If quantum mechanics were correct, they would break it. This became known as Bell's theorem, one of the most important results in all of physics. In simple words, either information travels faster than light, or particles don't have definite properties until measured. Either way, reality as we knew it could never be the same. Experiments that changed everything. Starting in the 1970s, physicists began to test Bell's inequality. The first convincing test came in 1981 by Alain Aspect and his team in France. They created pairs of entangled photons and sent them in opposite directions. Then, they measured their polarizations, the direction of each photon's vibration, at random angles. If local realism were true, the results should have followed Bell's limit. They didn't. Aspect's results clearly matched quantum predictions. The universe had spoken. Entanglement was real. Since then, more and more precise experiments, using photons, ions, and even entire molecules, have confirmed it beyond doubt. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for proving what Einstein doubted. The universe is non-local. What happens here can instantly affect what happens there, no matter how far there is. What does it mean? The truth is, we still don't fully know. Entanglement doesn't let us send usable information faster than light. It's not a communication channel, it's a correlation. But it tells us something profound about how the universe is built. It means that separation might be an illusion, that the whole universe could be one vast, interconnected quantum field. Every particle, every atom, every breath you take might be subtly entangled with everything else. When you move, in some tiny way, the entire cosmos shivers. Quantum reality and you. Entanglement isn't just theory, it's technology. It powers quantum computing, where qubits can exist in many states at once and become entangled to perform calculations impossible for normal computers. It's the foundation of quantum teleportation, where information about a particle's state is transmitted from one place to another using entangled pairs. And it drives the dream of quantum internet, where secure, unhackable communication could link continents with entangled photons. Each of these ideas began as science fiction, and each is now being built, step by step, in real laboratories around the world. So the next time you send a message across the globe, remember, the universe might already be doing that on a much deeper level, with no wires, no light beams, just pure, silent connection. Entanglement and consciousness. Some thinkers go further, wondering whether entanglement might even play a role in consciousness itself. Could the human brain, made of countless quantum particles, experience subtle forms of entanglement? Could awareness itself arise from quantum processes that bind our neurons together in ways we can't yet measure? These questions remain open, speculative, but fascinating. They sit at the boundary between physics, neuroscience, and philosophy. What we do know is that entanglement challenges the most basic idea we've always believed, that you and the world are separate things. Perhaps, at the deepest level, everything is one, a single pattern, endlessly reflecting itself. The fabric of non-locality. If you could see the universe from a quantum perspective, it might not look like empty space at all. Instead, you'd see a shimmering web of connections, a cosmic fabric of energy and probability. Particles wouldn't be tiny dots, but overlapping waves, interacting in invisible harmony. Every electron in your body would be part of the same vast field as every electron in the stars. Every photon of light that touches your eyes would carry a whisper of the Big Bang, still resonating from 13.8 billion years ago. At this level, distance is meaningless. The universe isn't built like a machine, it's built like a song. and every atom sings its note in perfect entanglement with the rest. The philosophical edge. Entanglement forces us to rethink reality itself. If observing something changes it, if distant particles act as one, then what does real even mean before we look? Some interpretations say the universe splits into countless versions each time a measurement occurs, the many worlds interpretation. Others say everything exists as potential until observation crystallizes it into form. And some, like the pilot wave theory, suggest hidden structures guide every quantum event. But no matter which interpretation you prefer, all agree on one thing. Reality is stranger, subtler, and far more connected than anyone imagined a century ago. Entanglement in daily life. You might think this has nothing to do with your ordinary world, your morning coffee, your heartbeat, your thoughts. But every chemical reaction, every neuron firing, every photon entering your eyes, obeys quantum laws. Quantum entanglement is happening all around you, all the time. It's what allows photosynthesis in plants to work efficiently. It's part of how birds navigate Earth's magnetic field. It may even influence how smell and vision function at the molecular level. You are a quantum system living inside a quantum universe, a conscious wave interacting with countless others, toward the infinite. So what does it all mean? Maybe, deep down, there are no separate things. Only relationships, patterns, and probabilities dancing together, the way ripples overlap in water. Entanglement is the universe's way of whispering. Everything is connected. You were never alone. And maybe that's not just science. Maybe it's also wisdom. Because understanding the universe isn't only about equations and experiments. It's also about wonder, the quiet awe of realizing that even across the coldest, emptiest space, connection never disappears. In the next chapter, Part 4, Quantum Worlds and Infinite Realities, we'll explore the interpretations of quantum mechanics, the many worlds, the hidden variables, and the theories that try to explain what really happens when we observe reality. We'll dive into the debate that continues even today. What is real before we measure it? So stay curious, stay calm, and remember, somewhere at the edge of the universe, your atoms are still in quiet conversation with the stars. This was Part 3 of Quantum Physics, explained slowly. The spooky action at a distance. Part 4, Quantum Worlds and Infinite Realities. Tonight, we enter one of the most fascinating questions in physics. What is reality made of, and how many versions of it might exist? The measurement problem. Let's begin with one of quantum physics' most fundamental mysteries, the measurement problem. In quantum mechanics, every particle exists as a wave of possibilities until it is observed. Before you look, an electron doesn't have a definite position. It could be here, there, or both at once, described by a mathematical object called a wave function. But the moment we observe it, that wave collapses. The particle chooses one outcome, one location, one reality. But why does this happen? What does it mean for something to exist in multiple states until we look? And most importantly, what counts as an observation? This question has haunted physicists for over a century, and from it, multiple interpretations of quantum mechanics were born, each painting a radically different picture of the universe. The Copenhagen interpretation, the classic view. The first and most famous interpretation came from Niels Bohr and his colleagues in Copenhagen during the 1920s. Bohr believed that reality doesn't exist in a definite state until it is measured. He said, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. In other words, quantum mechanics doesn't describe objective reality. It only describes what we can observe and predict. Before measurement, an electron isn't anywhere specific. It's only after interaction with a detector, a photon, or a human mind that reality becomes real. This was revolutionary. It meant that observation and reality are deeply connected. The universe is not simply out there. It's partly created through interaction with it. This view is practical and mathematically sound, but it leaves a haunting question. If there's no observation, does the universe even exist in any definite form? The many worlds, interpretation, infinite realities. In 1957, a young physicist named Hugh Everett III challenged Bohr's idea. He proposed something breathtaking. What if the wave function never collapses at all? Instead, every possible outcome of every quantum event actually happens, just in different, parallel universes. If you flip a quantum coin, in one universe it lands heads, in another, tails. Both outcomes exist simultaneously, but in separate branches of reality. This became known as the many worlds interpretation. Everett suggested that the universe constantly splits into countless versions of itself. Every decision, every particle interaction, every random event, all create new branches of the multiverse. In this picture, there isn't a single timeline. There's an infinite tree of possibilities, expanding with every tick of time. You are not just you. There are endless versions of you. Some made different choices. Some live in worlds where history unfolded another way. It's mind-bending, almost poetic. And strangely, it solves the measurement problem. There's no collapse. The universe simply evolves, endlessly branching, endlessly real. The implications of many worlds. Think about what that means. When you measure an electron's spin, up or down, the universe splits into two copies, one where you saw up and another where you saw down. You'll only experience one branch, but both exist, and both are equally real. That means everything that could happen does happen somewhere. Somewhere out there, a version of you is listening to this same video but paused halfway through. Another version never found this channel. Another version became a physicist, discovering new particles. Every possible path exists in its own quantum timeline. It's both humbling and empowering. We often wonder about what-ifs, but in the quantum view, those what-ifs are not imaginary. They are realities that coexist beyond our perception. Quantum decoherence, why we don't see multiple worlds. If multiple realities exist, why don't we see them? Why does the world appear stable, consistent, and singular? The answer lies in a process called decoherence. In the quantum realm, superposition, being in multiple states at once, is fragile. It only survives when a system is perfectly isolated from its environment. The moment it interacts with anything, air molecules, light, heat, or even your eyes, the wave function becomes entangled with countless other particles. That spreads the information, and the quantum behavior averages out. To us, it looks like the particle made a choice, but really, it just became part of a larger system we can't measure directly. In this sense, reality doesn't collapse, it diverges. The you that saw one outcome no longer has access to the others. Each world becomes separate, invisible to the rest, like ripples spreading across an infinite ocean. The observer's role, consciousness or physics. Some physicists once believed the observer's mind was essential to collapse the wave function. This led to the idea that consciousness creates reality, a notion that fascinated philosophers and mystics alike. But modern physics doesn't require awareness, only interaction. A photon bouncing off a surface counts as observation. The universe measures itself constantly through endless interactions between particles. Still, the mystery remains. If the universe is built on probabilities, then why do we experience only one sequence of events, one continuous flow of time? Perhaps consciousness is like a traveler, moving through one branch of the quantum multiverse, moment by moment. Our experience might be the narrow path we take through infinite realities. Hidden variables, Einstein's hope. Einstein never accepted randomness as a fundamental truth. He famously said, "God does not play dice with the universe." He believed there must be hidden variables, unseen factors that determine outcomes behind the quantum curtain. One theory that revived this idea was the pilot wave theory, proposed by Louis de Broglie and later developed by David Bohm. In this view, particles do have definite positions, guided by a pilot wave, a subtle quantum field that steers them. It's deterministic, meaning the future is already encoded in the present. The strange probabilities of quantum mechanics, according to Bohm, come from our ignorance of these deeper layers. Although this theory matches many quantum predictions, it adds hidden dimensions, unseen mechanisms that most physicists find unnecessary. Still, it remains one of the most elegant attempts to restore a sense of realism to quantum physics. The quantum multiverse and cosmology. Modern cosmology suggests that quantum principles don't just apply to atoms. They may shape the entire universe. The Big Bang itself could have been a quantum fluctuation, a tiny wave that became the cosmic explosion of space-time. Some cosmologists now think our universe is just one bubble among many in an eternal multiverse, each with its own laws of physics. Some may contain stars, galaxies, and life. Others may exist for a fraction of a second, invisible and unreachable. In this grand view, quantum physics isn't just a microscopic curiosity. It's the foundation of everything. Reality, on every scale, is a quantum event. The quantum mind hypothesis. There's another frontier where quantum theory meets mystery, the human mind. Some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that consciousness might arise from quantum processes inside the brain. They believe tiny structures in neurons, called microtubules, could host quantum coherence, maintaining delicate quantum states that influence thought and awareness. This is known as the orchestroir theory, short for orchestrated objective reduction. It suggests that our thoughts might not be purely biological, but partly quantum, that the mind might be, in a sense, a small quantum computer, capable of connecting to the universe's deeper layers. This idea is controversial, but fascinating. And even if it's not entirely correct, it reminds us that consciousness itself might be one of the universe's greatest quantum mysteries. The universe as a quantum computer. Some physicists, like John Wheeler, suggested that reality might fundamentally be made of information. He famously said, "It from bit," meaning the physical world, it, comes from informational choices, bit. Every interaction, every yes or no, every photon absorbed or reflected is like a computation. The universe could be seen as an enormous quantum computer calculating itself into existence. And if that's true, then the laws of physics are not just rules, they're algorithms. The universe might be both hardware and software, running on the code of quantum mechanics. You, me, the stars, all part of a grand cosmic computation. Infinite worlds, infinite reflections. Close your eyes for a moment. Imagine every possible version of you, living in every possible universe. One version became an astronaut, walking on Mars. Another became a poet, writing about the stars. Another is living a quiet life by the sea, never knowing the others exist. All these lives, all these realities, are part of the same infinite wave function. You are the melody played on an endless instrument, a single note in the symphony of the multiverse. And somewhere, out there, all your other selves are listening to this same story, falling asleep under the same cosmic sky. In the next chapter, Part 5, The Quantum World Within Us, we'll explore how quantum physics shapes life itself, from the way plants use sunlight to how your brain might use quantum effects to think. We'll dive into quantum biology, teleportation, and the strange overlap between physics and life. Until then, take one more deep breath. And remember, every possibility you've ever dreamed of may already exist, somewhere in the quiet, infinite expanse of the quantum multiverse. Part 5, The Heart of Quantum Reality, Superposition, Entanglement, and the Hidden Universe. In the last part, we open the door to the strange world of quantum theory, a world where particles act like both waves and dots, and where certainty seems to dissolve into probabilities. Now, we journey deeper, far beyond everyday logic, into the very heart of quantum physics. Here, things stop behaving like they should and start behaving like they could. Let's begin. The quantum superposition, when reality splits. Imagine placing a marble on a hill. In the classical world, our everyday experience, that marble must roll left or right. It can't do both. But in the quantum world, that marble doesn't decide immediately. Instead, it exists in a superposition, rolling left and right at the same time. It's like a coin spinning in the air. It's neither heads nor tails, but both possibilities hovering together until it lands. Quantum particles behave like that. They stay in a blended state of many possibilities, only choosing a definite outcome when we observe them. This is one of the most baffling ideas in all of science. Reality itself doesn't settle until it's measured. Take the double-slit experiment, one of the most famous in physics. When scientists shoot tiny particles, like electrons, through two thin slits and don't observe them, they behave like waves, creating an interference pattern as if each electron went through both slits at once. But when we look closely, when we measure which slit it passes through, the pattern disappears. Suddenly, the electron chooses one slit. It's as if the universe only decides what's real when someone is watching. This raises an almost poetic question. Does reality exist independently, or does it need consciousness to collapse it into existence? Schrodinger's cat, the symbol of uncertainty. To illustrate this, physicist Erwin Schrödinger proposed a thought experiment in 1935. Imagine a cat sealed inside a box with a radioactive atom, a detector, and a vial of poison. If the atom decays, a purely random event, the detector triggers and breaks the vial, killing the cat. If it doesn't decay, the cat lives. Quantum physics says that until you open the box, the atom exists in both decayed and non-decayed states, meaning the cat is both alive and dead at the same time. Of course, we don't see cats that are both alive and dead in our everyday world. So, the question becomes, where does the quantum world end and the classical world begin? When does the wave of probabilities collapse into a single truth? This mystery, known as the measurement problem, lies at the center of quantum mechanics. Some physicists say observation itself collapses the wave function. Others argue that interaction with the environment, like photons bouncing off the cat, does the job automatically. But no one truly knows where the line is drawn. Quantum entanglement, the cosmic connection. Now, let's explore something even more extraordinary: entanglement. Imagine two tiny particles, twins born from the same event, flying apart in opposite directions. Even when separated by light years, they remain mysteriously connected. Measure one particle's spin, and instantly, the other's spin aligns perfectly, as if they're still talking to each other across the universe. Einstein called this spooky action at a distance, because it seemed to defy relativity. How could information travel faster than light? But countless experiments have confirmed it. Entangled particles behave as one, no matter how far apart they are. This means the universe has hidden threads connecting everything, invisible cords woven through space and time. It's like two mirrors reflecting the same image from across the cosmos. Touch one, the other responds instantly. Some scientists even suggest the entire universe might be entangled, a vast, cosmic web of quantum connections linking every particle since the dawn of time. If true, that means you and I, this planet, the stars, everything, might still share faint echoes of quantum connection from the Big Bang itself. Quantum tunneling, escaping the impossible. In our world, if a ball doesn't have enough energy to climb over a wall, it stops. But in the quantum world, a particle can sometimes tunnel right through the wall, appearing on the other side as if by magic. This is called quantum tunneling, and it's not just theory. It's real and vital. It powers the nuclear fusion inside the sun. It makes transistors and computer chips possible, and it's used in devices like scanning tunneling microscopes, which let us see atoms directly. How does it work? Because particles in quantum mechanics are also waves, and waves can leak through barriers. Even if a particle's energy shouldn't allow it to pass, there's always a small probability that it will. Think of it like this: a ghost that sometimes slips through a closed door, not by breaking it, but because it never really hits it. That's the quantum world for you. Even the impossible has a chance. The quantum field, the ocean beneath everything. At deeper levels, particles aren't even little dots anymore. They're ripples in vast invisible fields that fill the universe, called quantum fields. Every type of particle, electrons, photons, quarks, is just a vibration in its own field. So, an electron isn't a thing moving through space. It's a disturbance in the electron field. Light is a wave in the electromagnetic field. Matter itself is frozen vibration. This is known as quantum field theory, QFT, one of the most accurate frameworks ever built. It explains nearly every particle interaction we've observed. The math is complex, but the idea is beautiful. The universe isn't made of things, it's made of waves of existence, overlapping and interacting like music in a grand cosmic symphony. And when we listen closely enough, those notes become the laws of physics. The observer's role. Does consciousness create reality? One of the most haunting questions in quantum mechanics is this: does the observer, the conscious mind, actually affect reality? When a measurement collapses a wave function, what truly happens? Is it just the physical act of interaction, or does awareness itself matter? Some physicists, like John von Neumann and Eugene Wigner, suggested that consciousness might play a role, that the mind, in some deep way, participates in forming the universe it perceives. Others firmly disagree, arguing that physics works fine without invoking awareness. But the debate remains open. If consciousness does influence quantum events, it could mean our minds are not just passengers in the universe, but quiet participants in shaping it. Every observation, every thought, could ripple through the quantum web, subtly sculpting reality. It's a profound idea, and one reason quantum physics feels more like philosophy of existence than just science. The quantum future, technology, imagination, and beyond. Quantum physics isn't just theory. It's the foundation for some of the most advanced technology humanity is building. Quantum computers use superposition and entanglement to process information in parallel, solving problems that classical computers might never solve. Quantum cryptography promises unbreakable communication, protected by the laws of physics themselves. Quantum teleportation, yes, it's real, already allows scientists to transfer quantum states instantly between distant particles. Each discovery brings us closer to a future that sounds like science fiction, a world of instant communication, near-infinite computing power, and perhaps one day, a deeper understanding of the link between reality and mind. But for now, quantum physics remains both our greatest achievement and our biggest mystery, a mirror reflecting not just how the universe works, but how little we truly understand it. So, as you listen, maybe while your eyes grow heavy, think about this. Every atom in your body once danced in the heart of a star. Every breath you take is shaped by quantum rules. And somewhere, in the infinite field of possibilities, another version of you might be doing the same. Listening, learning, wondering. The universe is stranger than we can imagine, yet familiar enough to feel like home. This is the beauty of quantum physics. It reminds us that everything is connected, uncertain, and alive with potential. Quantum physics doesn't just challenge what we know about matter, it challenges what we know about reality. And time is its strangest illusion. What is time, really? In classical physics, time flows like a river, smooth, continuous, always moving forward. But at the quantum level, time starts to look less like a flow and more like a pattern of probabilities. Imagine you could freeze the universe, zoom in, and watch reality unfold frame by frame. You'd see that every moment isn't smoothly connected. It's a series of tiny, discrete quantum changes. Some physicists even believe time might not flow at all. It may simply exist, like a landscape where past, present, and future all coexist. We only experience the flow because we move through it. Like walking through a 3D world, the world doesn't move, we do. In quantum mechanics, the laws of physics don't care which direction time flows. They work just as well backward as forward. So, why do we only remember the past and not the future? That's one of the great puzzles of physics. The arrow of time seems to emerge not from nature itself, but from entropy, the tendency of things to go from order to disorder. When you break an egg, it becomes a mess. But you never see a broken egg reassemble itself. That's entropy, the reason we perceive time as moving forward. Yet, in the quantum world, an electron or a photon can move forward and backward in time. It's only our macroscopic world, the one built from countless particles, that forces events to seem one-directional. So maybe time doesn't flow like a river. Maybe it's a vast ocean, and we're just waves passing through it. The quantum multiverse, infinite realities. Now imagine this. Every time a quantum event happens, like an electron deciding whether to spin up or down, the universe doesn't choose one outcome. It splits. In one universe, the electron spins up. In another, it spins down. Both are real, but now separated. This is the many-worlds interpretation proposed by physicist Hugh Everett in 1957. According to it, every possibility, every tiny quantum choice, creates a new branch of the universe. Right now, there could be countless versions of you. One who turned left this morning instead of right. One who chose coffee instead of tea. One who never watched this video. Each exists in its own timeline, invisible but real. And because quantum physics allows every probability to exist, the number of universes could be infinite. This isn't science fiction. It's one of the most serious theories in modern physics. It solves many of quantum mechanics puzzles by saying, the wave never collapses. Instead, every possibility continues, just in its own universe. Think about that. Right now, infinite versions of our cosmos might exist, some almost identical to ours, others unimaginably different. A universe where dinosaurs never went extinct. A universe where stars burn green. A universe where time itself flows backward. When you look up at the night sky, maybe you're not just seeing distant stars. Maybe you're seeing countless reflections of infinite worlds, all branching and overlapping like a cosmic forest. Quantum time travel, a dance of cause and effect. If the universe is a quantum system, and time isn't linear, could time travel be possible? Quantum physics doesn't rule it out, but it redefines what it means. At the smallest scales, particles seem to influence the past. In the delayed choice experiment, physicists found that how we measure a photon now can determine how it behaved in the past. That's not a typo. It literally suggests that a future decision can change a particle's history. So, does the future affect the past? Maybe not in the way we imagine, but in the quantum world, causality is flexible. Some physicists propose closed time-like curves, loops in space-time where an event could circle back to influence itself. Einstein's general relativity allows for this under extreme conditions, near black holes or wormholes. Imagine this. A quantum particle enters a wormhole, loops through space-time, and emerges before it entered. From one perspective, it traveled backward in time. From another, it never left. It's not that quantum mechanics allows paradoxes. It's that it defines reality so probabilistically that paradoxes simply dissolve. There's no fixed version of the past or future, just probabilities that coexist and shift with observation. So maybe time travel isn't about moving through time. It's about navigating the landscape of possibilities that time creates. The quantum vacuum, energy from nothing. Now let's explore something even stranger, the quantum vacuum. You might think of empty space as truly empty, but at the quantum level, even the vacuum boils with energy. Particles and antiparticles constantly pop in and out of existence, borrowing energy from the void and then disappearing again. This invisible storm is called quantum fluctuation, and it's real. We've measured its effects in laboratories. It's what gives rise to the Casimir effect, where two metal plates in a vacuum are pulled together because of energy differences in the space between them. This vacuum energy might even explain the cosmological constant, the mysterious force driving the acceleration of the universe's expansion, also known as dark energy. So, the emptiest parts of space aren't empty at all. They're alive with potential, a seething quantum sea of creation and destruction. It's as if the universe breathes, even when it looks still. Quantum biology, life at the smallest scale. Here's a twist. Quantum mechanics might not only explain the universe, it might explain life. In the last decade, scientists discovered that quantum effects play roles in biological processes once thought purely chemical. For example, in photosynthesis, plants may use quantum coherence to transfer energy perfectly, like particles taking multiple paths simultaneously to find the most efficient route. Birds may navigate using quantum entanglement in their eyes, sensing Earth's magnetic field. Even in human olfaction, our sense of smell, quantum tunneling might help detect molecular vibrations. This emerging field, quantum biology, suggests that life itself might depend on quantum mechanics working inside living cells. So, from the spin of an electron to the spark of consciousness, quantum physics might be the hidden script of life. Quantum mirrors, the universe looking at itself. Imagine the universe as a grand mirror, reflecting itself endlessly. In quantum mechanics, observation changes what's observed. So what happens when the universe observes itself? Physicists like John Wheeler proposed the participatory universe idea, that observers are not passive spectators, but active participants in reality. Every time a conscious being measures or experiences something, the universe becomes a little more defined. In this view, the cosmos is like a story being written and read at the same time. Stars form, galaxies spin, and consciousness emerges. And through consciousness, the universe learns about itself. Perhaps that's why it feels meaningful to look up at the stars. Because, in a way, the universe is looking back. Ring Planet 7. Imagination exercise, the quantum journey. Let's imagine something together. You're standing on a quiet hill under a sky full of stars. Every star represents a universe, one where something different happens. A breeze moves through the grass. In another world, it doesn't. You look up, and suddenly the stars shimmer, like possibilities collapsing and unfolding endlessly. Somewhere in that infinite network of worlds, another you is standing under another sky, wondering the same thing. The connection between you and them isn't light years apart. It's quantum entanglement across existence. Every decision, every thought, sends ripples through the cosmic web. And maybe, just maybe, those ripples are what make reality real. So what have we learned? That time might not flow, it might stand still. That reality may branch endlessly, creating infinite versions of the universe. That even empty space is alive. That quantum mechanics doesn't just describe the universe, it is the universe. It's the language the cosmos speaks, quiet, uncertain, but deeply connected. And as you let your thoughts drift, remember, even your dreams, floating somewhere between imagination and reality, are quantum possibilities of the mind. Every thought, every particle, every heartbeat, part of the same grand equation. The equation that says, existence is not certain. It's simply possible. The end of our quantum journey. And that brings us to the end of tonight's journey through quantum physics, explained slowly. From the strange dance of particles and waves, to the mysteries of time, reality, and consciousness, we've explored how the universe, at its deepest level, is more wondrous and connected than we can ever imagine. If you enjoyed this calm exploration of science and curiosity, please take a moment to subscribe to the channel, like this video, and share your thoughts in the comments below. Your support helps this channel grow and encourages more curious minds to join us in uncovering the secrets of our universe, one quiet night at a time. Thank you for watching Sleep with Science. Until next time, keep wondering, keep imagining, and keep listening to the universe.